very warm audience. Very few people. Okay, so I'm giving an unusual talk. Unusual in the sense that let me show you what my usual talk looks like very quickly. Because most of my talks don't actually have equations. But today you're going to see a lot of them. So this is a talk I gave to the national parks just last Friday, I think. Yeah. And there's actually a lot of mathematics in this. It's nonlinear dynamics, so I don't know whether MAS has a course on nonlinear dynamics. Dynamical systems. Anyway, this person is actually a mathematician, but he works in the ecology department. And he studies forests, and these are the various forests that goes through phase transitions. As the summer temperature warms, and so you see no equations. And then examples, words, no equations. Pictures, no equations. More pictures, no equations. More pictures, actually a lot of mathematics in here between regime shifts, but no equations. So this is what my typical talk looks like. I say things like autocorrelation and critical slowing down. Of course, you can do this mathematically. I can show a lot of equations, but I don't show. And that's because most of the time my audience are not mathematicians or mathematics students. And this, again, no equations, but a little bit of equations. That's it. Okay, so let me quit this thing and go on to the talk proper itself, which is why I care about determinants and why you should too. Okay, quit this and okay, let me see where we are. Here we are. And okay, so why should I care about determinants? I don't actually have a lot of materials, so I will talk very slowly. Or I can talk more about my PhD thesis project, and then I will have to spend 3 hours to explain to you what I did. But I can't really do that. So I just sketch some of the ideas and where determinants come in calculations that are done on a day-to-day basis by physicists. So I don't know how many here are mathematics students. One. All the rest are physics students. So I don't understand why mathematics students don't care about determinants. Okay, anyway, so that's what I'm going to talk about, determinants. And we start off with something that you all understand very, very well. You know, I also teach in the Masters in Financial Engineering program. I teach them calculus and linear algebra. And I teach them linear algebra first, then multivariable calculus. And when I go through Gaussian elimination, I tell them that for my exam, they need to perform Gaussian elimination at the speed of light. No, they will fail if they perform it only at the speed of sound. Okay, so they need to be able to just keep doing. Of course, this is a peanuts case. Anybody can do this. Usually, it will be something like a 4x5 matrix or a 6x5 matrix, and then they have to, finish the Gaussian elimination within about 15 minutes and then get the answer. And then the answer will then have to be plugged into a next part of the question where they have to do Lagrangian optimization. So things like that I usually throw at Masters in Financial Engineering students because they go out there and they have to make money for the company they work for. So if they are not good at doing this kind of computation, who can trust them with money, right? Correct? Yeah. So anyway, so why am I bringing up this particular example of Gaussian elimination? So this is the most generic system of two linear equations in two unknown variables that you need to solve. So if you follow through with the Gaussian elimination procedure, make this leading coefficient 1. So that's what we did in the first step. And then after that, we get rid of the sub-leading, the leading coefficient in the next rows, and then make it 1, and then finally get rid of this as well, and then this will be the final answer. And you see that the x is some weird combinations of bq minus dp divided by ad minus bc. Y is aq minus bp divided by ad minus bc. And you can start doing this right now if you want to. It doesn't take very long. But you see this factor AD minus BC appearing. Okay? And this is actually the determinant of the 2 by 2 matrix. So the coefficient matrix A, B, C, D you write the determinant this way, either with a det or with vertical bars, and this is the way you compute it. For a 2 by 2 matrix, very easy. Everyone should know this. You can close your eyes and do it. You must be able to do it like, if you must be able to have this level of proficiency if you are going to use this seriously in a job where money is at stake. So you take A, multiply by D, and you subtract B multiplied by C. So just a cross. I would have made a cross if I had to write this on the whiteboard, or I use a PowerPoint presentation, but LaTeX, I have under limited time, I can only give you something like this. So this is, anyway, this is the determinant of the 2 by 2 coefficient matrix. Now, so that's where you see the determinant appearing for a linear system of equations. 2 variables. What if you have n variables? N variables, n equations, all linear. Will the determinant appear? And the answer is yes. It appears generically. But how do you calculate such a determinant? So if I have 3 by 3, you know, how do I form the crosses? So it turns out that there's a special recipe for doing that, and it is called Laplace expansion. Okay. So you guys are taking MH2801 right now, right? The physics students. So have they started talking about determinants yet? Yes. So you've learned about the Laplace expansion. Huh? Cofactors. Okay, you're talking about cofactors. But I mean, they're all related. And there are some physics students who graduate without knowing that this procedure is called Laplace expansion. Very common, you know. We just remember, this is how we do it. We don't give it a name. We don't bother to give it a name, although we give other crappy things names, or we don't give this a name. But there's a name for this procedure, Laplace expansion. So if you have an n by n matrix, those matrix elements are listed down here. The way to evaluate its determinant is to do this iteratively. First, you start off with the first row, or if you don't like the first row, you can also start from the second row. So you can start from any row, any column, but traditionally people start from the first row. Later on, when we talk about properties of determinants, that will allow you to actually do some manipulation of the matrix before you actually start computing the determinant. There was one exam question I set for the MFE students where the computation of the determinant is extremely easy after you perform Gauss-Jordan elimination. So you have to do some things to the matrix before you calculate the determinant. But if you don't do that, then you end up doing you take a long time just to compute the determinant. Anyway, so let's say we start from the first row, A11. So we put a plus sign down here for A11, and then form the minor that is accompanying A11. So the minor, to get the minor associated with A11, what you do is you get rid of this column, get rid of this row, and then what is left behind you write as the determinant of a smaller square matrix. Okay, n by n minus 1 by n minus 1. And then in the first row, the next matrix element is A12. Now you put a minus sign. You always alternate the signs. Okay, plus, minus, minus. And then you get rid of the first row because it's A1. The row index is 1. The column index is 2, so you get rid of the second column. And then now you're left with a little bitty here and just something like a column vector over here. So you have to patch them back up together to form the minor, which is A21 and A23, and then all the way to A2n, and that's the minor. That's the minor that you have to evaluate. Okay, and then you keep doing this. I forgot to put the plus ... So you keep doing this until you reach the last matrix element. This sign here can be plus or minus depending on whether n is even or odd. But you do the same thing. You get rid of this column, you get rid of this row, and then the remainder is you form the determinant of that smaller matrix. Okay? Now, of course, you don't stop here. You don't stop here. What you do is you continue Laplace expanding all the determinants until you're left with nothing. So you've expanded till the determinant is the determinant of a single number. And then single matrix element, and then you can stop. So in this procedure, you can see, if you think about it a little more deeply, that you end up with many terms. So how many of you can tell me how many terms you end up with? In general, so let's say we have no zeros that will kill terms. How many terms will you end up with? N, huh? N, I can't hear you. N terms. Actually, it's way more than that. First step already n terms, so you cannot have possibly n terms left at the end. So way more than n terms. So how many terms are there?
Okay, if up to the first step are n terms, how many up to the second step?
Okay, so then after the second step, you will have n times n minus 1. Because all these guys have, you will produce n minus 1 terms. All of them produce n minus 1 terms. And then you have a minor that is n minus 2 times n minus 2. You expand it again, you get n minus 2 terms. So the number of terms you end up with is n times n minus 1 times n minus 2 times n minus 3 all the way to 1. So the number of terms you end up with is n factorial. Okay? So n factorial terms. And each of the terms, okay, you also find that because, after I take A11, right, after I take A11, I've eliminated this column, eliminated this row. So in the remainder of the minor that I'm going to evaluate, in fact, all terms that I get from expanding it, I am never going to find another matrix element from the first row or the first column. Do you agree? Agree, right? So that means that, every row and column appear only once in each of those n factorial terms. Okay? So if you think about it some more, you can understand even more things. But let's now go on to do a proper definition of the determinant, or proper to a physicist, maybe not proper enough for a mathematician. But since I don't know the proper mathematical definition, so I have to just stick with this. Okay, so it's fine. Okay, so so we've talked about this already. N factorial terms after it's fully expanded. Each fully expanded term is a product of n matrix elements, because after you expand it, you find that each of the term contains n matrix elements. Each row appear only once. Each column appear only once, and then the sequence of columns is a permutation of the sequence of rows. Okay, so some ways of rearranging the rows to get the sequence of columns in each of the terms in the final Laplace expansion. So the determinant of the n by n matrix can be formally defined as a sum over all permutations of n numbers, and then there is this sign of the permutation, and then sum over all such products. So ai and a permutation where what appears in the ith position in the permutation, and the sign will be plus or minus depending on whether the permutation is odd or even. Now, since there are mostly physics students here, maybe I can just try to explain a little bit more what it means for a permutation to be odd or even. Suppose I look at 1, 2, 3, and I look at 3, 2, 1. Is 3, 2, 1 an odd or even permutation of 1, 2, 3? What does that mean, right? What does that mean? Maybe I can go on the board and start writing. It's great that there's a board here, but I also have to watch the time. So 1, 2, 3, and 3, 2, 1. So what do I need to do in order to get 3, 2, 1 back into 1, 2, 3, or 1, 2, 3 back 1, 2, 3 into 3, 2, 1? So I'm allowed to interchange elements a certain number of times. So what can I do? First of all, and I think the rule is that I can only interchange adjacent numbers. So if I change this once, that's one permutation. And then after that, I do 2, 3, 1, the second permutation. And then 3, 2, 1, the third permutation. So this is just this guy here. I think this is what I learned when I was a first year undergraduate at NUS.
Actually, it doesn't matter. You can interchange 3 and 1
Uh-huh. So it's still odd, right?
Yeah.
So in the end, it is still odd because you need an odd number of permutations to get here. How about something like this? How about 2, 3, 1? How do you get 2, 3, 1 from 1, 2, 3? So how many permutations must you make pairwise? So obviously, I can do 2, 1, 3, and then I can do 1, 2, 3. So altogether, 2 permutations. So this is 3 permutations, 3 or 1 permutations. So this is odd. So this guy here is considered an odd permutation of 1, 2, 3. And this is considered an even permutation of 1, 2, 3. So if you have n numbers, you can work out all the total number of permutations. In fact, there are n factorial of them, just nice, just the correct number for writing out the Laplace expansion. And we also know that what the sign is, okay? So the sign is determined by whether it is an even or odd permutation of the n numbers, okay? So permutation means it can only interchange pairwise. You cannot take 3 and change them all at once. That's not the right thing to do. And so you just remember this definition, which is, in the sense you can, it's motivated by the Laplace expansion. In the history, I don't know too much about the history of the determinant. So I don't know whether they discovered this formula first or they discovered the Laplace expansion first, and then therefore they generalized the definition to something like this. So most likely it's the other way around. So they actually did the computation and then found that this is the formal definition. Okay? So, of course, you don't define things that are not useful. And in fact, the determinant is very useful. It always appears in the solution of a linear system of n equations in n unknowns. Okay? Always. So if you do Gaussian elimination, you may not actually notice it. Okay? So that's why we're going to talk, first we're going to talk about properties of the determinant, and afterwards I'll talk about a method of solving linear equations that engineers learn, but physics students and mathematics students don't learn anymore. Because it's, I don't know why they don't learn anymore. But I'll talk about, comparison between that other method and Gaussian elimination. So the properties of the determinant, let's say we take one row in the matrix A, the coefficient matrix A, and multiply it, all the matrix elements by k. So how does the value, how does the determinant, what is the value of the determinant of the new matrix? And it turns out that if you remember that the determinant of the new matrix, if you do a Laplace expansion, every term in the Laplace expansion contains the modified column only once, not twice, not 3 times, not n times. And therefore, you know that the determinant must therefore just be multiplied by a simple factor of k, not k to the n. Okay? Because every row only appears once. So it doesn't matter whether you're doing it for the row or doing it for the column. If you're doing it only for one row, then k appears as a unit factor. So it's not raised to the power of n. Okay? So unlike, for example, the calculation of eigenvalues. Okay? But usually eigenvalues, you multiply the entire thing. So, and also, the second thing, if we interchange any 2 rows of the matrix A to get a new matrix, let's say I have n by n matrix, I take the row I and row j and I switch them. Okay, it doesn't matter which rows I switch. It doesn't matter whether I'm switching row I, whether row I is even, row j is even, row I odd, row j odd, row I even, row j odd, row I odd, row j even. I will pick up a minus sign. Okay? Any interchange of rows will give me a minus sign. And if I find 2 or more identical rows or columns in the matrix, then the determinant becomes 0. Okay? And I'll talk about why that is so just shortly afterwards. And if we add k times of row j of A to row I of the matrix A to get the new matrix, then the determinant is not changed. Okay? Now, if you take note of these 3 things that I talked about, actually these are the 3 elementary row operations that you use actually in Gaussian elimination. And why is it that you do Gaussian elimination? Do you know why you do Gaussian elimination? I want to solve for the unknowns, right? So why am I doing Gaussian elimination? Ah. So can I just say I have 3 by 3 matrix for the three equations in 3 unknowns. I just throw away one equation and then I try to solve the other 2. Why can't I do that? Why must I follow a strict recipe like the Gaussian elimination?
Well, actually, you can do it like that. I mean, you
No,
can
wait, but
express one of the variables from the last equation in terms of the 2 variables.
yeah.
So then you substitute it.
Yeah, but that's still one form of Gaussian elimination. We're talking about just throwing away one equation completely. So I don't know whether I don't know how many of you actually understand that Gaussian elimination produces a sequence of a linear system of equations which have exactly the same solution. How many of you understood that? That means from the obviously. Okay, so it's important, that's why it's important to check that the determinant has this particular properties, because otherwise, Gaussian elimination will produce the unique solution, but the determinants will not obey that kind of relationship between the sequence of equations that are produced by Gaussian elimination. So this, you see that this is row interchange. This is actually no, this is not. What is this? There's scaling. This is scaling. This is row interchange, and this is addition of rows. So we pretty much just the elementary row operations in Gaussian elimination. That's supposed to guarantee that the solutions do not change as you muck around with the coefficient matrix. Okay. Now, other properties of the determinant is that if I take the transpose of the matrix and I find its determinant, it should be the same as the determinant of the original matrix, because I didn't change anything. I actually changed the order. But when I do the Laplace expansion, I just find that this particular term just appears in a different place in the Laplace expansion for A transpose, but otherwise, term for term, they are identical. Okay, just the order is scrambled. And also, the determinant of a product of matrices is the same as the product of the determinants. This is not so easy to prove, but it can be proved. Most good linear algebra textbooks will prove it. Most bad linear algebra textbooks that physics students use will not prove it. But you'll be told that this is true. Okay, and it's good to keep this in mind. That this, once you have this, you can do a lot of amazing things. You may not see it now, but when later on in quantum mechanics, you will actually make use of this. Because we test for commutation between operators. Yeah. Okay, so let me see what time it is now and whether I need to speed up or slow down. Okay, so I'm nearly halfway. So I haven't talked about it yet. So now, I'm sure all of you learned Gaussian elimination, but over the other side in engineering school, they learn another method to solve linear equations, and that is Cramers Rule. So how many of you know about Cramers Rule, apart from the mathematicians? Okay, so Cramers Rule is very simple to apply. What you do is you form this matrix equation of the 2 by 2 equations, and then Cramers Rule tells you that the solutions are given by the ratio of determinants. So the bottom is of course the determinant of the coefficient matrix. The top determinant is a hybridized matrix. So what you do is you take the constant vector and you stick it in the column which correspond to the matrix. Correspond to the unknown. For example, x. Which column multiplies into x? So obviously it is the first row, right? So the second row will never multiply into x, it will multiply into y. So therefore you take PQ and you stick it into A and C. You form this new modified matrix and you take its determinant, and this gives you the answer for the solution of x. And same thing for y, you just stick it into B and D, replace B and D by P and Q, and you form the determinant, divide by the determinant of the coefficient matrix, and this is your answer. So this Cramers Rule applies to n by n matrices as well. And in fact, the engineers learn this method to apply to maybe systems of equation that are, say, 3 by 3, 4 by 4, 5 by 5 until a certain number, but not too big. So you never see in exam engineering students, electrical engineering students solving 100 by 100 determinant. It will take 2 hours for them to finish, and then you'll be wrong. Then they have to do it again. Okay? So, and you can see that, it pretty much has the same structure of the solution that I've derived in the first slide. And this is not commonly used, at least not commonly used in a computer, because it is actually less efficient than matrix decomposition methods. So I don't know whether in MH2800 you learn about matrix decomposition methods. Or do the math students learn about matrix decomposition? Huh? Do you guys teach the math students matrix decomposition? No? No, that's the physics students, CNM student. Yeah. Well, I mean, if the maths PhD student doesn't know about matrix decomposition, that means you guys didn't teach those.
This is linear algebra 1. They must.
So the standard way is to decompose a dense coefficient matrix into an upper triangular, lower triangular, so that you can do backward substitution, forward substitution in succession. So that is n square as opposed to n cube for Gaussian elimination. But you have to make sure that you have the decomposition ready. The decomposition itself is n cube. But if you use the same coefficient matrix many times, then you have savings. If you do it once and then you solve it once and you have to solve another coefficient matrix, then there's no savings. Okay? So there are, depending on whether the matrix is symmetric or asymmetric, there are various decomposition methods. So, and in fact, the matrix diagonalization is based on a decomposition method. I don't know whether the students learn it. So,
Diagonalization probably not yet.
I know not yet, but I don't know whether they learn QR when they start talking about diagonalization. Because I teach the MFA students QR in order to explain why it converges and what are the limitations and stuff like that. So that's a third year course. QR, no. Okay. So anyway, I'm running short of time, so let me bring you back. Now, it's different area in mathematics. So this is probability and statistics, and obviously you know something about the normal distribution. It's probability density is given by this formula down here. This is for a normal distribution that has mean mu and variance sigma square, and obviously any probability distribution must be normalized. So I write the normalization condition in a weird way. So instead of writing the integral of this thing equals to 1, I write the integral of the exponential equals to square root of 2 pi sigma square. Now, you will see the reason for me doing this weird thing soon. And then when you evaluate the expectation of functions of the random variable x, this is how you do it. You divide by the normalization constant, and then integrate from minus infinity to infinity that function multiplied by the exponential factor that appears in the normal distribution. Okay, so far it should be standard stuff. If you have not seen this before, for physics students, don't worry, you'll see it a lot of times when you start doing higher level courses. But it's not so fun if you deal with just one random variable. For example, if you want to go into a bank and take people's money and invest it and make sure that you don't lose all of it, you need to at least be able to handle a multivariate normal distribution. So MFE students learn this they should be able to recite the formula for the multivariate normal distribution even in their sleep. And so what happens is that we have n random variables. We arrange them as a vector, and then the means of all these n random variables will be arranged into a vector of means. But because there are n variables, so we don't just talk about variances, we also talk about covariances. So the sigma matrix, this is arranged as a matrix, n by n matrix. This is the so-called the covariance matrix. Some people call it the variance covariance matrix. But a covariance matrix is clear enough. Everybody knows what we are talking about. And the matrix elements are actually the expectations of these two products. So the xi minus mu I, xj minus mu j, this will give you sigma ij. But what appears in the multivariate normal distribution is the inverse of the matrix, not the covariance matrix itself. And of course you understand why, because if I go back, you see that the variance appear in the denominator. So you need the covariance matrix to somehow appear in the denominator. And sometimes very sloppy physicists will write divide by a matrix. Yeah, and of course, you know, you don't understand what it means to divide by a matrix. So any time you see a physicist write divide by a matrix, you actually, what they want you to think is multiply by the inverse.
On the left or on the right?
That shouldn't matter, right, if it's a square matrix.
It doesn't matter. No, different, don't it?
Huh?
Even in MATLAB, if you divide by a matrix, there are different notations.
No. Okay, MATLAB is different. MATLAB understand the division in a different way. So I'm talking about when people write theoretical papers and they divide by a matrix, that usually just means multiply by the inverse matrix.
Yeah, but then you can multiply on the right with the inverse matrix or on the left. There are different things.
Here it is. I think here is clear because it's not multiplication by. Here it doesn't really matter because you can multiply by this guy first or multiply this one. Here it doesn't matter because this is a symmetric quadratic form. Okay, so this is effectively this whole combination is supposed to mimic this combination when you have n random variables, and this is of course very important in financial engineering. If you don't know this well enough, you can cause financial crisis. Okay, so you must know this well enough so that you can protect, safeguard your investors' money. Okay, and but the problem is, of course, I write this as proportional. I did not write down the normalization constant. So how do you get the normalization constant, which is a n-dimensional integral of this exponential factor? Any suggestions? Throw into Wolfram alpha. Okay, Wolfram alpha will not be able to do. I think will not be able to do this symbolically for you. If you give it a number, you know, if you give it some actual coefficient matrices here, these can be, you know, symbolic. It may be able to do it for you, but you know, we're hoping that, you know, the students we train are you know, smart enough that they should be able to look at this and say, okay, I know what I need to do. Okay, which is one of the reasons why calculus and linear algebra is in the same course, MH2800, because this is multiple integration, and this is linear algebra, the diagonalization of a symmetric matrix. So when you don't know how to deal with n by n matrix, but if you see that it is symmetric, so the first thing you do is just try your luck, diagonalize it. Okay, so the covariance matrix is not just symmetric, it is actually positive definite. So all its eigenvalues are positive. So you actually, it's a very nice matrix. So after you diagonalize it, you will get, you know, a matrix of the eigenvectors multiplied by, you know, this is the matrix of eigenvectors. This is the transpose of the matrix of eigenvectors, and this is a diagonal matrix with all the positive eigenvalues. And these are actually the variances, the principal variances of the system of random variables. And of course, if this is the covariance matrix, and I want the inverse, so how do I get the inverse? The inverse is something that when you multiply to sigma again, gives you the identity. So what you need to understand first is that these matrices of eigenvectors, they are orthogonal matrices. O times O transpose is the same as O transpose times O and gives you the identity. So if you multiply O by its transpose, whether you're multiplying on the left or the right, you always get identity. So the way to, you know, if you try this combination, multiply it in here, what you will find is that, let me see, something is wrong. Is it correct? I think I may have written something wrong here. Yeah. So there's transpose here and no transpose here, so that, you know, the O's will kill each other, and then lambda inverse times lambda is 1, and then after that goes away. Then the orthogonal matrices are going to cancel each other again, so you get 1. So this is I mean there's a typo here. The transpose is over here. There's no transpose here, and so some of the things here may be wrong, but let's not worry too much about small typos. And what you do is you redefine a new set of random variables that are a linear transformation of the original set. Okay? Now, and then of course you have to remember, in evaluating the normalization constant, you have to integrate over the old random variables. So when you change to new random variables, you must be able to integrate over the new random variables as well. And in MH2800, you will learn about how to change integration variables when you go from one set to the other set, it involves something called a Jacobian. Okay? And if these two variables are related by a linear transformation, then the Jacobian is just the absolute value of the determinant of the transformation matrix. In this case, O. Okay? So linear doesn't mean that it has to be, the matrix does not have to be orthogonal. It can be just any kind of linear transformation, but it always takes on this particular form. The Jacobian is just a number, and it's obtained by taking the determinant of the transformation matrix and then taking the absolute value. So you see another place where the determinant appears. To prove this, I've actually done this for the MFE students. You can do it. You have to think about volumes in high-dimensional spaces. So if you do that, you can actually prove that it automatically involves the Jacobian, which is the determinant. Okay? So the nice thing, of course, is that this determinant is 1. Because if I take the determinant of OO transpose, then it's the same as taking the determinant of the identity. The identity has only 1s in the diagonal, 0s everywhere else. So if you do the Laplace expansion, you only get 1 term left. And that is a product of all 1s, so it just gives you 1. So that tells you that the determinant is either plus or minus 1. But here you're taking the absolute value, so it's just 1. So therefore, this is just this guy. And then finally, you change the factor in the exponential, this particular factor in the exponential, to y transpose lambda inverse y, which is actually, if you actually multiply it out, you find that the n random variables, the new random variables, they are now no longer multiplied together. So if you have an exponential of this sum, you can just split them into n different exponentials, and then you can do your integration one term at a time. So that's the whole strategy. I already talked about it in words. I need to make sure that I don't run over. Okay, I still have some time. Okay, so the first step, change of variables, change of integration variables. Second step, break up the integrals into term by term by term by term by term. And this is where we make use of the earlier normalization condition that we've written down. So if I integrate an exponential, a Gaussian exponential, over from minus infinity to infinity, I just get square root of 2 pi, whatever thing that appear here. Okay, if there's no 2 here, you need to divide by 2, but since there's a 2 here, I just bring this guy and stick it in here. Okay, so same thing, this is what happens here. You see that this is y1 squared over 2 lambda 1, so I just take lambda 1 and stick it here. Here, this is lambda 2, I take lambda 2 and stick it here. And then, of course, all the way up here, this is lambda n, I stick it here. And I can combine all the factors of 2 pi. So there are n of those. So 2 pi to the n over 2 power, n over 2. And then the lambdas I can combine. I can just form a product of all of them. And then this has to be raised to the 1/2 power. Okay? So, and also, if you consider what the diagonal matrix lambda looks like, you see that, the determinant, again, it's just the product of all its eigenvalues. So this is another, useful property that you can remember, that the determinant of a diagonal matrix is just the product of its diagonal matrix elements. In fact, you can show to yourself the diagonal of a triangular matrix is just the product of all the diagonal matrix elements. The rest of the matrix elements don't even contribute at all. Okay? So and therefore this is the determinant. So let's finish writing it. So this is the determinant of lambda. But the determinant of lambda, you see, this is the determinant of lambda. But the determinant of lambda can be rewritten in terms of the covariance matrix, sigma. And after we have split them using the property that I've described earlier on, you get the determinant of O raised to 1/2 power, determinant of epsilon raised to 1/2 power, determinant of O transpose raised to 1/2 power, and both of these are 1, so you're just left with the determinant of the covariance matrix. So if someone gives you a very complicated looking covariance matrix, or I give you a big data set and you have to compute the covariance matrix, and then fit it to a normal distribution, a multivariate normal distribution, it is actually very easy. It's actually very easy because the normalization constant is just the determinant. And if you stick this to MATLAB will give you the determinant in less than a second. Okay, unless it's really huge. So therefore, you can finally write down the joint probability distribution for multivariate normal distribution in this particular way. Okay, so this is what the MFE students learn, and then I have a few more slides to show you where else do determinants appear, where in the working life of a physicist. So this is where else the determinant appears. If we are studying a system of n electrons in quantum mechanics, and then we want to look at the total wave function, then because the electron is a fermion, and therefore it is it's a completely identical, indistinguishable system of particles, we have to make sure that under exchange, it is either symmetric or anti-symmetric. So the symmetric kind we call a boson, anti-symmetric kind we call a fermion. And fermions, in order to write down their total wave function, we need to write it as in terms of a Slater determinant. So all these are single particle wave functions, phi 1, phi 2, phi n, and they can be filled with electron 1 or electron 2 or electron all the way up to electron n. But in actual fact, the ground state or any state must be written in this particular form. Okay? So that, so why do we write it in this particular form? Why? Because if I take xi, I take the ith electron, and I interchange with the jth electron, then effectively I am doing a interchange of rows in the Slater determinant wave function, and I will pick up a minus sign. So that is what I want, because I want the sign of the wave function to change when I do interchange of electrons. So this will, in the new physics syllabus, it will probably be covered in quantum 1. But now, no. Now it's not covered. It's only covered in quantum 2. Okay? But of course, before you graduate, before physics students can graduate from us, they should know something about indistinguishable particles like this. Okay? And the other thing is a little bit more fancy. So this will be not for undergraduates, but for PhD students going on to do string theory or particle physics. And that is, this is one way of thinking about quantum mechanics. That is, we talk about wave functions. There's another way to talk about quantum mechanics that is in terms of bras and cats and abstract Hilbert spaces. And there's a third way of thinking about quantum mechanics. Actually, there are more ways, but the third, more popular way of thinking about quantum mechanics, and that is to think in terms of path integrals. That is introduced by Feynman. Because Feynman talks about particles, quantum mechanical particles, that are neither bosons or fermions. Okay, or rather more boson than fermions. For fermions, because of this property of interchange, anti-symmetry, we actually cannot use, we have to write down Gaussian factors that are not Gaussians of ordinary numbers, but Gaussians of Grassmann numbers. So this is called a Grassmannian path integral. And these numbers are very interesting. So if you multiply psi I and psi j, it's the same as multiplying psi j and psi I and putting a minus sign in front of it. You can't put a number to it. You cannot say that psi j is equal to 0, because 0 is an ordinary number. These are Grassmann numbers, but they have this kind of algebra, anti-commuting algebra. Now, and in a sense, they mimic the behavior of the fermions themselves. And if you multiply two identical, Grassmann variables of the same kind together, you just get 0. And here, if you make sure that A is anti-symmetric, then this integral gives you the determinant of A, okay, to the square root. Now, let me show you why this is interesting and surprising. Okay, so here is what we'll talk about. Here it is. So if I integrate this guy here, I get the determinant to appear in the denominator. But if I integrate it for a Grassmann Gaussian integral, I get it to appear in the numerator. So that is the kind of distinction that you make, and it appears in quantum field theory of fermions. Okay? So I won't have time to talk about this. So this is a lot of interesting, fun mathematical exercises involving Gaussian integration, involving Grassmann integration, involving block block diagonalization of a matrix, but let's not worry too much about it. And so before I end this talk, what time is it now? Okay. So before I end this talk, let me tell you something about determinant-like objects in physics. Okay. So I've already said that the ground state wave function of n fermions is a Slater determinant. So instead of writing down the big, matrix, I can just use the definition of the determinant to write it in this particular way. So the total wave function of n fermions will be just a sum over all possible permutations of n fermions with the sign of the permutation and then the single particle orbitals and the particular electron that you're talking about. So this is how the total wave function of a system of n fermions look like. Okay? Then you walk into Rayner's lab. Suppose you walk into Rayner's lab. So how many of you know who Rayner is? Rayner. Nobody knows who Rayner is. How many of you know who David Wikowski is? Also don't know. Okay, these are two physics professors here, and they work with cold atoms. So they use lasers to cool the atoms down to very, very low temperatures. When I say low, that means, nanokelvins. So just 10 to the minus 9 Kelvin above absolute zero. And of course, when you cool them down to this kind of temperatures, the atoms become communists. So they lock face. They do everything together. They move together. They shake together, and they do whatever things that ordinary atoms do, but they do it now all together because they're now in a state of matter known as a Bose-Einstein condensate. Okay, and but of course, usually, normally when you talk to Rayner, then he will tell you, okay, we will do this kind of laser cooling for atoms that are actually bosons. Okay, so they're not fermions. You don't want to cool. You can also cool fermions, but most of them prefer to cool bosonic atoms, so that they can form the Bose-Einstein condensation at higher temperature. If it is a fermionic atom, then you have to cool it down even lower, maybe picokelvins, before you can get it to condense. But of course, ultimately, these atoms are atoms. So they're bosons, but they cannot actually sit on top of each other because they are made up of fermions themselves. They're just composite bosons. And therefore, in theory, when we do theory, we just say that, these are hardcore bosons. Hardcore just means that they behave in all respects like bosons, except that they cannot stack on top of each other. Okay, there are other bosons that can stack on top of each other. If you do third year statistical mechanics, you will learn about photons, which are bosons that can stack on top of each other. You will learn about phonons, which are bosons that can stack on top of each other. But the kind of bosonic atoms that Rayner and David Wikowski play with, they cannot stack on top of each other. And also, again, you have to write down their total wave function. And then if you write down the total wave function, you find that very similar. Very similar, except no sign. No alternating signs when you go to different products of the orbitals. So if you are doing mathematics, if you see something like this is a matrix element, this is a matrix element, what is this particular combination of matrix elements called? And it turns out that it is called a permanent of the matrix. It is rare in the sense that, so far only physicists have found a way to use it. So I don't know whether mathematicians know of what kind of things they can do with a permanent of a matrix, but physicists know that it represents the ground state wave function of n hardcore bosons. Okay? And in order to get from here to here, you have to do something called a Jordan-Wigner transformation, which is a baby string theory. Okay? So in order to get a boson from a fermion, you have to form a string of fermions, and that is a boson. Okay? So I think that's all I have to say. So in conclusion, I hope to impress on you that determinants appear in many, many different places. First of all, in the more boring place, solution of linear system of equations. In the guise of Cramers Rule, even if you do Gaussian elimination, it's still there, just that you don't see it, you don't think of it as being there. And then it appears in the normalization constants of ordinary multivariate Gaussian integrals. It also appears as in the normalization constant of Grassmannian Gaussian integrals. It also appears in when you change integration variables. and then it appears in terms in the wave function, total wave function for n fermions. Okay, and then of course determinant computations and manipulations are important. So you should learn them as you would eat your vegetables, because they are good for you, right? So you need your daily nutrition of your vegetables, so you also need your daily dose of determinants. Okay, so that's all I have to say for today. You have any questions? No questions?
I have a question actually. This single electron orbital,
Yeah.
pi I, is it just theoretical, or is the formula for this function known?
Oh no, they depend on what system you are talking about. So if you're talking about solid, where am I?
You know, like Rayner and.
In Rayner, in Rayner's experiments, these are actually atomic orbitals. So if you can cool hydrogen.
Do they know it exists in the formula?
No, they don't.
No?
Yeah, because for those kind of many particle, many electron atoms, these kind of things can only be calculated approximately. But let's say if you have a solid, infinite solid, then all these are complex exponentials. They are all of the form EIK 1x. Yeah, they're all of this form.
So they're all of a similar form, right?
Similar form, but different K. Yeah. So that for those who will study, so those who will study solid state physics 1, solid state physics 2, then you will learn about the total wave function of a system of electrons, but you will probably not hear the instructor talk about Slater determinants. But fundamentally speaking, that the wave function is still a Slater determinant. Yeah. But so this is generic. Even sometimes we do not know what the orbitals are. And of course, not just physicists care about this. The chemists also care about this. Pinaki also cares about this, because he actually tried to compute this kind of things through Monte Carlo methods. And the problem with Monte Carlo method is that once you pick up a minus sign, you have a problem. They call this the minus sign problem for quantum Monte Carlo. And then for
why?
Because for important sampling in Monte Carlo, you need to treat the numbers as probabilities, not as amplitudes.
Okay.
Yeah. But if you square it, then you lose. You have a problem. Then you either don't get the sign, or if you keep the sign, then you cannot treat them as probabilities, and you don't know how to design the update. Yeah. So chemistry people also care about this thing here, because they are the ones who calculate the orbitals for multi-electron atoms. Yeah. So you should care too. Physics students should care too. Math students should know that the determinant is this powerful and appear in so many places. But there are unfortunately no math students here, apart from the PhD student. Okay.